Hey folks, we're back for Bennett's Chemistry 12 tutorials. We're starting the redox unit today, which there's a lot of components to it. So today's class is going to be just an introduction to it. It's not a quick introduction to it, but it will be an introduction to it. And what we'll do is we'll go over two kind of critical things. Number one, we'll go over what is it, because it'll be something new. You've seen reactions that are actually would be considered in the category of redox reactions. You just didn't know what they were doing there earlier on in your chemistry career. And then two, what we're going to do is we're going to look at a concept whereby you can tell if a redox reaction has occurred, and it's being able to identify what the oxidation number is of an atom, and then be able to identify what that atom did as a redox reaction was going on, okay? And then from there, there's a whole bunch of other things that we're going to explore later on in this unit. Okay, so what is redox? And redox, the actual word redox isn't really a word. It's just what people say as an abbreviated form of a reduction-oxidation reaction. So reduction, oxidation. And so instead of saying reduction oxidation all the time, people will just say redox, or you might hear someone pronounce it as a redox. And so this is it's a category of chemical reaction, and what it truly is, and we'll try and keep it simple first. What it truly is it's a chemical process where electrons are exchanged from one atom to another. That's all it is. And so you probably learned this way back in Science 9. It wasn't referred to as a reduction oxidation or a redox reaction, but you learned a little bit about atoms and their stability, and probably introduced the idea of a Bohr model and full outer shells and things of that nature. Well, actually, we'll return to that a little bit. It's not quite that simple, but we will return to that to just kind of build upon what you previously knew. Okay, so a redox reaction is a reduction-oxidation reaction. Now, what does reduction and what does oxidation mean? So those two words are obviously critical. And so each one of them it's a process. Okay, so a reduction is a process and oxidation is a process. And so we're going to start with the definitions of those processes, and then we'll start looking a little bit more in detail and tie it into what you previously have known about chemistry and reduction oxidation without really knowing it. And then we'll take it a step further. So reduction, first of all, is, and that's the symbol I use for definition. Reduction is a process during which an atom gains electrons. Okay, so let's go through this a little bit more in detail. So it's a process, so it's something that happens over time. And it's during which an atom, okay, so a single atom, so this is something important to keep in mind as we move forward. It may not make total sense yet, but the idea is that atoms gain electrons when they're undergoing a reduction. So you have to stop thinking of a whole molecule. You have to start thinking of the atoms within a molecule. And that will help you kind of along the way. And we'll talk about that a little bit more when we get into oxidation numbers here in a minute. We'll review this concept. So a process during which an atom gains electrons. And so sometimes it is an atom that wants to gain electrons. Sometimes it's an atom that's forced to gain electrons. And that's also a critical part of moving forward, that idea of does it want to? Is it being forced to do it? Is it ending up being stable? Is it becoming less stable? Things of that nature. So we'll get into those details later on. But essentially, a reduction is that process. Now, I want you to think for a second here, before I even write down what the definition of oxidation is. A reduction is a process during which an atom gains electrons. You might say, from where? You don't just gain electrons out of the ether. Like they don't just arrive and the atom picks up electrons from somewhere. They have to get them from somewhere. And so in your mind, you're probably thinking there's got to be another part to this. You can't just gain electrons without something losing electrons. Well, guess what? This is why it's called a redox. And it's always together. You don't just usually just say, well, we have a reduction reaction. And we don't have an oxidation reaction. We have a redox reaction because you've got part of it is the gaining of electrons, but then there's the other part of it, and that's the oxidation. So the definition of an oxidation is very similar to what a reduction is. So a reduction is a process. Well, so is an oxidation. It's a process during which an atom, and you probably guessed it, loses electrons. Now I've put plural in there. It couldn't be a single electron. So there's two parts here, and you probably anticipated that when you looked at the definition of a reduction, that if something gains electrons, some other atom had to lose electrons. And so essentially a redox reaction are these two parts that are required of each other. If one is going to gain electrons, another one had to lose electrons in order for that to happen, right? So if you start thinking about a redox reaction and you tie it into your reaction kinetics from the beginning of the year, if one atom bumps into another atom and electrons transfer from one to the other, one loses them, one gains them. Well, that process is a redox reaction. Okay, and so the redox reaction is the two processes put together. A nice way of thinking of a redox reaction is the reduction is one half and the oxidation is the other half. And you put those two halves together and you get the whole overall process, which is known as a redox reaction. So let's take a real brief look back in time. When you first learned about Bohr models and you learned about atomic stability and things of that nature. And I'm going to take an atom of sodium. So I'm going to take an atom of sodium and I'm going to draw a Bohr model. And I'm not going to review Bohr models, I'm just going to draw it. So Bohr model, sodium has 11 protons. The first shell for a sodium has 2 electrons. The second shell has 8 electrons. And then the third shell of sodium has a lone electron sitting on the outer shell. Then I'm going to take a fluorine and a neutral fluorine. And a neutral fluorine has 9 protons. Has 2 on the first shell. And it has 7 on the outer shell. So back to, I think, Science 9 is when you first learn how to do a Bohr model and how you draw the shells and things of that nature. And you were introduced to that concept of stability. Atoms like to have full outer shells. So this lone electron that's sitting on the outside of the sodium, on the third shell, and the missing electron there for the fluorine, well, the reason why these two things react and do what they do is because when they bump together, in order to gain stability, as we probably told you in Science 9, that electron pops over there. And so they have to collide hard enough to force that electron to go. Of course, sodium likes to lose that electron, and fluorine likes to gain that electron. And so the electron actually moves from there. Whoops. Not from there. Hello. The electron moves from there to there. And essentially what happens is this sodium then loses that third shell And instead of being a sodium neutral atom anymore, it's now turned into a sodium + 1. And because the fluorine picked up an extra electron, that's no longer a neutral atom of fluorine. That is now an F-. The two stick together and they make sodium fluoride. And so you get the formation of an ionic compound. Well, that is a redox reaction because what happened is the sodium lost an electron, and so it did this. It oxidized. The sodium went from being neutral to being +1. It lost an electron. It oxidized. The fluorine went from neutral to -1. It gained an electron, and so therefore it reduced. Now, kind of an interesting, I guess, play on words really, or the semantics of it, is that fluorine gained an electron and yet it reduced, right? And so that, in terms of what reduced means in the world, that kind of doesn't quite make sense unless you think of its charge. So it reduced, meaning it went from 0, neutral, down to -1s. Like on a number scale, it went down 1. And so if you go down, you are reducing. So if your charge goes down, you are being reduced. The only way you can go down in charge is by picking up negative charges, right? So if you were at +3 and you went to +1, well, you went from +3 to +1 because you picked up 2 negative charges. Therefore, you must have reduced. And sure enough, +3 to +1 is a reduction in the charge. And that's kind of a nice way of remembering this concept, okay? Now, in reality, this fluorine that's over here would have probably gone around as, instead of just an F, it probably would have gone as an F2, which means, I'm going to draw it a little bit smaller here. Which means that 2 fluorine atoms would have been bound to each other by overlapping their orbitals and forming a covalent bond. Okay, and so those 2 electrons that are right there in the Bohr model, sorry, I'll move my pen a little bit so you can see it. The 2 electrons that are right there are actually bonding electrons, and so they're sharing those 2 electrons. Atoms of fluorine don't really want to share. They would prefer to have an electron all to themselves. But sharing those 2 electrons in a covalent bond is a better option than not having them at all. And so they float around in this F2 format because it's better than being individual and having like an open space entirely. And so this is how they exist. Of course, given an opportunity to pick up an electron, they absolutely 100% do it. And so if a sodium comes around, and it's 11 protons, and one of the electrons will go to one of the fluorines. And so say this top fluorine will say, well, see you later, buddy, I'm skipping town, and I'm dropping that partner, and I'm picking up the electron from that sodium that just arrived. Well, if there's one sodium to donate an electron, there's probably another sodium. Oops. That's willing to donate to the other fluorine. And so chances are there's going to be 2 sodiums to donate 1 electron per sodium, to go to the two fluorines that are there. And when that happens, you get an actual reaction where each sodium oxidized by giving up one electron, each fluorine reduced by one to go to fluoride, and you ended up making two. And so that's an actual chemical reaction. Like, that's a balanced chemical reaction right there. Two sodiums and a fluorine in its diatomic gaseous form react, they form two molecules of sodium fluoride, because this guy gave up an electron, became Na plus 1. This guy gave up an electron, became Na plus 1. So now there's two Na plus 1s because the sodium oxidized. Each of those fluorines that used to be in a covalent bond, they've now both picked up an electron, they've both reduced, and so they became F negative 1. The F negative 1s attached to the Na plus 1s, and they form two perfect little NaFs. And so the formation of ionic compounds from the elements, a synthesis reaction, is an example of a redox reaction. Of course, if you reverse this, if you took sodium fluorides and you made this reaction go in the opposite direction, which can happen if you actually heat it up enough, you can actually decompose that thing. The sodium will pick up the electrons again, and the fluorine will lose those electrons again, and they'll go back to their original form. Okay? So now hopefully you're starting to think, well, okay, so both directions of a redox reaction are in fact redox reactions themselves. So if it's a redox in the forward direction, it would be a redox in the reverse direction as well. And to even think a little bit further ahead, you might start thinking, well, which way is more spontaneous? Like, which way does this thing actually want to go? And you're probably thinking, the two elemental forms, like sodium doesn't like to be in its elemental form. It's got an extra electron on the outer shell. It doesn't like to do that. Fluorine is missing an electron on its outer shell. It doesn't like to do that. And so these two things are not in a stable, happy form in terms of their atomic electronic structure. And so they probably love to do this reaction and form sodium fluoride. They probably hate to go back in the other direction and like move the electrons back the other way. That process could still, in theory, happen, but it really doesn't want to happen. And so you can start thinking about the spontaneity of each direction of that redox reaction, which again, we're going to get into later on. And there's a way of telling, is that going to be a spontaneous or a not spontaneous process? And if it's a certain degree of spontaneity in one direction, what is that degree in the opposite direction? And the two are obviously related to each other. Okay, so the basic concept is that a reduction-oxidation reaction is one where an atom loses electrons, those electrons go on to another atom, that atom reduces. And so the redox reaction is the combination of the two. You can't have one without the other. Sodium wasn't going to oxidize unless it had something to download the electrons onto. Okay, so that's kind of the general principle of all of this. Okay, let's get into the second question that's up here. So the what is redox? There's a couple of things that you're expected to know. You're supposed to be able to just kind of describe what redox is, and then you should be able to define what reduction is and what oxidation is, which the definitions were just up there. So now let's get a little bit more detailed. Okay, let's kind of get behind the curtain and actually take a look at the details of what's going on here. So one of the first questions you have to be able to do or answer, there's actually two questions. So how can you tell, two questions. One, if a redox reaction occurred. And then two, what reduced and what oxidized. Now you might say, well, I think it's kind of obvious sometimes. If you understand that an oxidation is losing electrons, therefore its charge goes up during the process, and a reduction is gaining electrons, therefore its charge reduces or goes down as the process goes on, then you can kind of just look at the reaction. But sometimes it's not that simple to see what happened. Sometimes you're not even talking about ionic compounds. So let me give you an example. So I'll just give you one little example here. And then I'm not going to answer it right away. There's going to be some, we'll return back to it. So for example, it's probably a reaction that a lot of you have seen over the years, either in your Chemistry 11 or even previously, right? This is a hydrocarbon combustion, as you would have been taught back in Science 10. So CH4 is methane, reacting with oxygen, so it's burning, it's combustion, and it's producing carbon dioxide and water, as all hydrocarbons do. So first of all, this is a redox reaction. Well, how do I know? Like, how can I tell what this happened? None of these things up here are ionic compounds. They don't have a charge necessarily. And so to be able to understand, one, is this thing even a redox? Like, prove it to me that this is a redox reaction. That's part of it, yes. But even more kind of deeper than that, which atoms underwent oxidation and which atoms underwent reduction? Like, what actually happened here? And when the atom reduced, how many electrons did it gain? When the atom oxidized, how many electrons were lost? And to be able to give a little bit more of a detailed description of what that process looked like. Okay, so to be able to do that, to be able to look at this thing and say, this atom did this, and this atom did this, and this atom did nothing, what you need to be able to do is you need to be able to assign what's called oxidation numbers. Okay, and so I'm going to erase this. I'm going to come back to this one, and we'll kind of look at it once we go through this oxidation number concept. So we're going to assign what's called oxidation numbers. And so why are oxidation numbers important? One, you're going to be able to look at it at a compound or individual atoms, and you're going to be able to say, okay, this was its oxidation number before the reaction occurred. Here's its oxidation number after the reaction occurred. This is what happened to its oxidation number. This is what it did. And so if it started before the reaction at -3, and it was still -3 after the reaction, that atom didn't do anything. Like, it was along for the ride. It was a spectator. It didn't really participate in the redox reaction. But if something went from +5 to -1, well, +5 to -1, that's a reduction. It reduced. Not only did it reduce, but it reduced by 6, which means that that atom picked up 6 electrons. Okay, so you're going to kind of use these things to be able to understand kind of what happened behind the curtain, okay? So to dig deeper into it. So what is, in fact, an oxidation number? An oxidation number, I don't necessarily want you to think this is the charge of something, because if you say it's the charge of something, charges are typically reserved for ions. Like, ions have charges. So, sodium +1 has a charge of +1. Oxide has a charge of -2. Those ions have a charge, and it's like a full charge. But covalent compounds are sharing electrons. They don't have a charge, right? So you don't say the charge of a carbon in a carbon dioxide is this, because it's not really an ion. So you don't assign charges necessarily. However, oxidation numbers are kind of like that concept, okay? So an oxidation number, I like to think of it as this. An oxidation number is what charge would an atom have if you took the compound, ripped apart all of the atoms from it, like took every single atom and tore it all apart. So if I had, let's use the methane as a perfect example. If I took CH4. Okay, it has 5 atoms, 1 carbon and 4 hydrogens. If I actually could physically rip that hydrogen away from the carbon and rip all those hydrogens away from the carbon. Just physically grab them and like pull them apart. The electron's got to follow one of those atoms, right? Like, so the electrons, if I pull the carbon and the hydrogen apart here, the two electrons that are represented by that line, the bond that's between them, those two electrons got to go somewhere. They follow one of the two atoms. Well, which atom do they go to? Right? So that's kind of a harder question, because what if you're talking about two nonmetals? Well, two nonmetals pulling on, you rip them apart, where do the electrons go? And so you're going to start thinking about your electronegativity and which one holds on to electrons a little bit better. And so an oxidation number would be, well, what charge would that hydrogen have if you ripped it away from the rest of the molecule? Where would the electrons go and what would the charges be? And so every single individual atom, and that's really critical to understand, every single individual atom will have an oxidation number, even if it's within a compound. Okay, so CH4, the carbon has an oxidation number. The hydrogens, each of those hydrogens, has an oxidation number. Now, the hydrogens are all going to be the same because you'll see that they tend to behave in a similar way. So if I pluck all 5 atoms, rip them all apart, where would the electrons go and what would the resulting charges be if you could do that? Now, it's hypothetical, of course. Okay, and so that's what an oxidation number is. Now, if you're talking about an ionic compound, so if I'm talking about, well, let's use our sodium fluoride. So if that was my compound, well, if I draw that thing, it's an ionic compound. Well, how do I draw it? Well, okay, I'll draw it like this. So it's actually a stable sodium ion that has lost an electron, kind of sitting right there, and a stable F fluoride, F minus ion, sitting right there, but they're stuck to each other. Static electricity, it's electrostatic force, positive, negative. They don't really care that the other one's there, right? They're already separated from each other from an electronic perspective. They're only stuck together because they're oppositely charged. That's why they're stuck together. So if I rip them apart, electrons aren't going anywhere, they've already gone. So this bonding here doesn't really matter. So ionic compounds, the charges of the ions are the oxidation numbers, okay? And that's obviously kind of critical, okay? So really the challenging part of this is when you've got covalent compounds. Now, how do you go about assigning oxidation numbers? Okay, so there's a process to this. There's a hierarchy out there in the universe. And so I'm going to write that hierarchy down. It's like a priority list. Okay, so when you're looking at a compound and you say, okay, I have to assign an oxidation number here in order to find out what it did during this process. You have to go through, okay, where am I on the hierarchy here? And I'll kind of show you how it applies. So we're talking about okay, so I've got the species, so what we're talking about, and what its oxidation number is. So an elemental atom, okay, so one that has not lost or gained electrons, it's floating around, it is neutral, right? It has a charge of 0. Elemental atoms always have an oxidation number of 0. So regardless of what you have, so if you have elemental gold, Au, right? What charge is written in the top right-hand corner here? Well, nothing's written. That means it has a charge of 0. So that gold atom has an oxidation number of 0. What if you're talking about a diatonic element? So you're talking about H2, right? Because hydrogen gas floats around, it's diatomic. And so you've got 2 atoms of hydrogen bonded to each other. covalently bonded. So what is the oxidation number of that? Well, each atom of hydrogen in that molecule of diatomic hydrogen has an oxidation number of 0. Okay? It doesn't matter what you have. If you have octatomic sulfur, again, the charge up there is 0. Well, if the charge is 0, that means all 8 of those atoms covalently bonded to give you an octatomic sulfur molecule, they're in elemental form. Every single one of those atoms has an oxidation number of 0. Okay, so elemental, we're talking 0. Monatomic ions is the next one. Monatomic ions, I can't really write something over here because the oxidation number is the charge, whatever the charge would be. So if you have a, I don't know, an Fe plus 3, well, the oxidation number of Fe plus 3 is plus 3. You will also sometimes hear it has an oxidative state. And so, like the oxidative state or the oxidation number of an Fe plus 3 is plus 3. Okay? It can be complicated by having it in an ionic compound. So instead of Fe plus 3, let's say I have, whoops, Fe Cl3, so it's an ionic compound. Well, that ionic compound is really the combination of a couple of monatomic ions. The monatomic ion Fe plus 3, and then what is the anion there? Well, it's Cl minus 1. Now, granted, there's 3 of them in that compound. There's 3 chlorides in there. But the oxidation number of the iron is plus 3. The oxidation number of the chloride is minus 1 because they're monatomic ions. Okay? What if you had K2SO4? Well, K2SO4 is an ionic compound. It is made out of K plus ions. You've got 2 of them because of the subscript. And then it's made with a polyatomic ion of SO4 minus 2. Well, SO4 minus 2 is not a monatomic ion, right? It's a polyatomic ion. It has more than one type of atom that's in there. It's sulfur and oxygens all kind of smushed together to give an overall charge of minus 2. Okay, so the oxidation number of the sulfate is not negative 2. The sulfur in that compound, or in that ion, would have an oxidation number. The oxygen in that polyatomic ion would have an oxidation number. The only thing I can say for certain is that the K has an oxidation number of plus 1. Okay? So you've got to look for monatomic ions because whatever their charge is, that's their oxidation number. Okay? So now the next thing on the list, because those are kind of, those two are right off the top. Your elemental, you're 0. If you're a monatomic ion, your charge is your oxidation number. Now, you start getting into a couple of interesting things. Number one is fluorine. And I'm going to say fluoride because if it's in a compound, you'd be calling it something fluoride. Even if it was covalent, it'd be something fluoride. Right? So fluorine is the most electronegative thing in the universe. Right? It is like literally the granddaddy of all atoms that are out there. It is, for lack of a better way of putting it, it's a complete electron bully. It steals electrons from everything. Right, so if you go back to that concept of oxidation numbers are what charge would something be, even if it was covalently bonded, and you rip them apart. So if you take a fluorine attached to anything else and you rip it apart, that fluorine takes the electron. I don't care what you attach it to. You attach it to carbon, attach it to oxygen, attach it to hydrogen, attach it to chlorine, attach it to anything. You rip the fluorine away from something, it's taking an electron with it. Period. Which means that the oxidation number or oxidation state of fluoride in any compound is -1. You'll see how we use this priority in just a minute. Okay, so that's really high on the list. The next guy are alkali metals, and you might say, well, yeah, but that's an ionic compound, so of course they're going to be +1. But you'll see there's one situation in particular where you have to know that the alkali metals have higher priority than something else, and I'll show you that in just a minute. The next one on the list is hydrogen. Now, of course, we're not talking about hydrogen in its elemental form. If it was elemental, hydrogen would have an oxidation number of 0. We're talking about hydrogen when it's bonded to something else. So hydrogen is going to have a charge of +1. Unless it is attached to something higher on the priority list. And then the thing higher on the priority list gets its charge and tells hydrogen what it's going to be. Okay, so, and I'll show you that situation in just a little bit. Next one on the list is oxygen. And oxygen has an oxidation number of -2. So oxygen gets to be what it wants to be, -2, unless it's attached to something higher on the list, and then it kind of takes the second seat, I guess, as it were, if it's attached to something else. And again, I'll show you situations where it has to play the understudy. Next on the list, and kind of the last thing on the list that we're going to put on here, are nonmetals. And in order of electronegativity. Okay, so what order of electronegativity are we talking about? Well, the general rule of thumb is that electronegativity tends to increase on the periodic table as you move, which way am I going here? As you move right, that looks left, as I move right and up on the periodic table. So if you're talking about the nonmetals, all the atoms that are to the right of this staircase that's on the periodic table, they're the things that tend to gain electrons. And so the more electronegative something is, the more it tends to pick up electrons. So if you go back to what is the concept of an oxidation number, imagine you've got two nonmetals. Let's say you've got phosphorus attached to a chlorine. And don't worry about the bonds being filled properly or not. You just got a phosphorus and a chlorine. The oxidation number concept is if you took those two atoms and ripped them apart, so there's two electrons holding them together. If I rip them apart, where do the electrons go? Who gets the extra electrons? And so what happens is if those two things are battling for electrons in the bond and you rip them apart, the one with a higher electronegativity will tend to take the electrons from the other one, whether it wanted them or not. Phosphorus also likes to gain electrons. It's a nonmetal. It likes to gain electrons, but so does chlorine. So if you physically rip them apart against their choice, one of them's got to take the electrons. Well, the one that's stronger, meaning electronegative, will take the electrons. And so where on the periodic table are these two relative to each other? Okay, so chlorine is further up and to the right of phosphorus. And so it has higher electronegativity than phosphorus. And so that's the general rule of thumb. I guess the real rule of thumb is to look at the electronegativities. But if you're just looking at a periodic table, up and to the right, the highest electronegativity. Of course, you're ignoring the noble gases. Noble gases don't want electrons. They're already stable. So they're not going to be in chemical bonds anyways. So what's the most electronegative thing in the universe? Well, fluorine, because fluorine's in the top right-hand corner of the nonmetals. So fluorine, sure enough, is way up here, right? It's the most electronegative thing. It does what it wants to do. And so it will grab an electron if you rip it apart from another atom. Now, what oxidation number do you assign to those nonmetals in order of electronegativity? Well, you assign there, and I'm just going to write this down, their preferred negative charge. And this is where you kind of resort back to your Science 9 understanding of atoms. So if you're talking about a nonmetal, you're talking about the atoms to the right of the staircase on the periodic table. You probably figured out somewhere along the way that the number of electrons that a nonmetal needed to gain to become stable, get a full outer shell like a noble gas, was how many positions or columns away from the noble gases it was. So noble gases are way over on the far right-hand side of the periodic table. One column to the left of that were the halogens, and halogens like to pick up one electron and form a charge of -1, because they're one column away, one electron, they full outer shell. One column over, group 16, that's the one that's headed by oxygen up at the top. They like to pick up 2 electrons because they're 2 hops away from the noble gases. Nitrogen, which has, it's 3 hops away, and the group 15 nonmetals, they pick up 3 electrons. They like to be -3. And so how many places away from the noble gases a nonmetal will be is what its preferred negative charge is going to be. Okay? Now, having said all of that, like this order of priority, how do you actually go about applying this to figure out what an oxidation number is? And then let's use it to figure out if a redox reaction occurred. So I'm going to erase it because I've got it in my head. So I'm going to erase it to give myself a little bit more space. I'm gonna just kind of show you how to apply this in a bunch of different situations. So the first one I'm going to use is this guy. So I'll use one that I just used. So PCl5. Okay, so that would be called Phosphorus Pentachloride. Okay, that's its name. Now, this is the molecule. What is the molecule's overall charge? Well, because nothing's written in the top right-hand corner for the overall thing, it has an overall charge of 0. Keep this in mind. Charge of the molecule equals the sum of the oxidation numbers. That's really critical to kind of keep in your mind. Oxidation numbers are per atom. You add up all the oxidation numbers per atom, they should come out to the charge of the overall molecule. So PCl5, what do we got? We've got 1 phosphorus, we've got 5 chlorines in there. Right? 6 atoms. If you take the oxidation number of the phosphorus and each of the 5 chlorines, you add those things up, they should come out to the overall charge of the molecule, which means they have to add up to 0. So the phosphorus plus the 5 chlorines has to add up to 0. So that is kind of critical because it's the little mathematical thing that you're going to do in your head. Okay? So keep this in mind. Total charge equals the sum of the oxidation numbers. So then you look at PCl5 and you say to yourself, okay, so what have I got in here? Which of those 2 takes priority, the phosphorus or the chlorine? And that's where you kind of look on your list and you say to yourself, okay, so it's not elemental. I'm going through the whole thing. It's not elemental. We're not talking about monatomic ions because this is a covalent compound. Phosphorus is non-metal, so is chlorine. So we're not talking about monatomic ions. We don't have fluorine. We don't have an alkali. We don't have hydrogen. We don't have oxygen. Oh, we've got nonmetals. So phosphorus and chlorine are 2 nonmetals. The order of their priority is due to their electronegativity. So then you go to your periodic table and you look for the one that's further right and up towards the fluorine. Well, chlorine's 1 position away from fluorine, and phosphorus is actually quite a bit away. So chlorine has higher electronegativity. So chlorine gets the charge that it wants to be. So what oxidation number does the chlorine have? A chlorine atom, a single chlorine atom, has an oxidation number of -1. So you see what I did there? I didn't put like it has a charge or something. I'm scribbling it above the molecule. Each chlorine has a charge of -1, but there's 5 of them. So the charge due to the chlorines would be 5 times -1. So it's almost like you say, well, the total charge equals 5 times the chlorine plus 1 times the phosphorus. Because you've got five chlorines and you've got 1 phosphorus. So mathematically, you can actually come up with a little equation if you like this. You can come up with a little equation. I don't. I do it all in my head and it saves time. I don't have to write it all down. But it's nice to think of it this way. So you've got the total charge is 0 because the molecule of PCl5 is 0. And then the chlorines are -1, which is going to be -5. And then plus 1 phosphorus. Okay, so 0 equals -5 plus the phosphorus, which means the phosphorus must be plus 5. Okay, so I did the math in my head. So if the chlorines are -1 each, that means the phosphorus must be plus 5 to make the overall molecule 0. And that's kind of how you do it in your head. So the phosphorus is plus 5. Phosphorus has an oxidation number of plus 5. You might say, oh, goodness gracious, phosphorus really doesn't want to be plus 5. But remember what an oxidation number is. It's if you pluck all the atoms apart, where do the electrons go? Well, the electrons follow all the chlorines because they're the highest electronegativity. The poor phosphorus gets left behind with getting 5 electrons taken away from it, and it's kind of sitting there going, oh, well, that sucks. And so that phosphorus has an oxidation number of plus 5. You might, again, be looking ahead and saying, well, okay, if that phosphorus has an oxidation number of plus 5 and it really doesn't want to be plus 5, maybe this compound is actually quite reactive because of that oxidation state of that phosphorus. And you're starting to think a little bit more in terms of the chemistry that comes from this. Okay? So that's how you assign the oxidation numbers to the PCl5. Okay, now I'm going to put a bunch up here on the board, and then I'm going to go through them, and I'm going to go through them fairly quickly, okay? I'm not going to write down the little equation. I'm going to go through what's in my head, and hopefully you'll kind of see how it all works, and hopefully you'll get fast and good at this. Okay, so here are my examples. So I've got ClO3 negative, got NH3, OF2, N2O4, C2H5OH, KNO3, and H2O2. Okay, so when I'm assigning oxidation numbers, what I'm doing is I'm going through and I'm using in my mind, I've got the priority list that's in there, okay? And I'm just going to, with my blue pen, I'm just going to scribble up above. These are not formal charges in any way, shape, or form. I'm just writing the oxidation number above each atom, okay? And remember that when I write a little number up there, it's per atom. Okay, so the first one I'm going to do is this guy over here. So the ClO3 -1. So I've got a chlorine and I've got 3 oxygens. You put all those oxidation numbers together, they have to come out to -1. Who gets priority, oxygen or chlorine? Oxygen's higher on the priority list. Oxygen's -2. So I'm writing a little -2 above the oxygen. So there are 3 of them. So the the total charge from the oxygens is 3 times -2, -6. For the whole thing to come out to -1, the chlorine has to be +5. Okay, so 3 oxygens, 3 times -2 is -6, +5 for the chlorine comes out to -1, and so you've got a chlorate ion. Okay, next one, NH3. You've got 1 nitrogen, 3 hydrogens. The overall molecule is neutral. It has a charge of 0 because nothing's written there. Highest on the priority list is hydrogen. Hydrogens get a charge of +1, and so I've got oxidation number of +1 for the hydrogen, higher priority. There are 3 of them, that's +3. The nitrogen, there's just 1 nitrogen, so they have to balance off that charge. So the 1 nitrogen has to be -3, oxidation number of -3. Next one down, the OF2. So again, I've got a neutral compound, because there's no charge there. I've got 1 oxygen, I've got 2 fluorines. Highest priority goes to fluorine. Fluorine gets an oxidation number of -1. There are 2 of them, so -1 times 2 is -2. I've got a single oxygen that has to balance off that charge to make it neutral, and so the oxygen is +2. That's probably a pretty reactive thing because oxygen +2, that's an oxidation state that oxygen really doesn't want to be in. And so it's going to, anything that it can bump into to get out of that oxidation state probably will. So this guy's probably pretty reactive. Okay, so that's kind of how it applies here. Next one, N2O4. Again, it's a neutral compound, 0. Their highest priority goes to the oxygens, which are -2. There are 4 oxygens, so -2 times 4 is -8, which means that the nitrogens over here, there's 2 of them, they have to come up with a total charge of +8, right, to balance off the -8 from the oxygens. So they have to come up with +8, but there's 2 of them, which means each individual nitrogen is +4. Okay, so the oxidation number of a nitrogen atom is +4. There are 2 of them, therefore it's +8. That balances off the 4 oxygens, which give a total charge of -8. So they balance to give you 0. Okay, so that's critical that you have to be thinking per atom. Okay, the next guy. This is ethanol. So there's carbons, hydrogens, oxygens all over the place. There's 3 different things. You follow the exact same rule of thumb here. It's just you've got 3 things. And so what happens is you'll assign priority to the first thing. You'll give it its oxidation number. You'll be left with 2 different atoms. Then you assign the next highest priority. And then you'll be left with the 3rd atom, which kind of gets, it's almost like you see it as being given the scraps, right? So whatever has the lowest priority gets the scraps of what's behind. And so who knows what it might be. I mean, sometimes you can even have an oxidation number that's a fraction. Like you'll come out to, well, your oxidation number is +3/4 or something like that. Okay, so that does actually happen. So don't be surprised if it actually happens. So let's go through this one. Okay, so I've got carbons, hydrogens, oxygen, and another hydrogen. All those hydrogens, consider them the same thing. So instead of 5 and 1, think of them as you've got 6 hydrogens. Okay, so who has highest priority between carbon, hydrogen, and oxygen? You've got to know your list, and so the list is hydrogen is first. And so if you've got a hydrogen, they're +1. So the hydrogens here are +1, so is that guy over there, +1. Now you're down to carbons and oxygens. Again, you have to assign a priority to those 2 things. And then we'll add it up and see what's remaining. So who has higher priority between oxygen and carbon? Oxygen does, and the oxygen's -2. Okay, now this is sometimes where writing down the numbers you won't make a silly mistake. Right, if you're trying to keep all this in your head, sometimes it's difficult to keep track of all the numbers. So you can write it down if you want. So here's kind of what you would be writing down. You'd say to yourself, I've got 6 hydrogens. They're all +1. So the hydrogens are contributing +6 to the molecule. Okay, so hydrogens are contributing +6. That oxygen, there's just one of them. That's -2. So far I have +6 and -2. So far I've got +4. That means that the carbons, the 2 carbons that are remaining, have to have an oxidation number that brings this molecule out to, it was neutral. So it comes out to being neutral. Okay, so far I have +4. That means the carbons have to come up with a total charge of -4 to make that neutral. There are 2 of them, which means each carbon has to be -2. And so the oxidation numbers in ethanol, the hydrogens are +1, the oxygen's -2, and the carbon is -2. Okay. Next guy down, KNO3. First thing you have to recognize is that this is an ionic compound where the K is actually a monatomic ion, right? So this thing is actually, it's almost like I like to think of it actually as it's 2 ions. So it's K +1 and NO3 -1. Okay, so the K is a monatomic ion of +1. Okay, and even if you go through the priority list, you're still going to get this right anyways. So the K is +1. It's monatomic ion. It happens to be stuck to NO3, but it's a monatomic ion with +1. The NO3 -1, therefore, now you've got this thing that is covalently bonded together with an overall charge of -1. So who gets priority? Well, the priority goes to the oxygen. The oxygen is going to be -2. I'm going to put it down here on the NO3 -1. So the oxygen is -2. There are 3 of them. That makes this -6. That means the nitrogen, to make the NO3 -1 come out to a total charge of -1, means the nitrogen must be +5. Okay, so the potassium is +1, the oxygen is -2, and the nitrogen is +5. Has an oxidation number of +5. Okay. The last guy, H2O2. So, and this is kind of a tricky one as well. So H2O2, again, it's neutral. Who has higher priority, hydrogen or oxygen? Hydrogen does. Hydrogen has highest priority. So hydrogen gets +1. There are 2 of them. So 2 times +1 is +2, which means the oxygens have to come up with a charge of -2 in total. There are 2 oxygens, so -2 divided by 2 is -1 each. Now you may have heard of this before. This is hydrogen peroxide, right? So stuff you clean your earlobes with when you're cleaning off your earlobe to put your earring in. So hydrogen peroxide. Peroxide is an actual oxygen ion, so an oxide, but it's with a charge of -1. So if you put oxygen with something of higher priority, so something like hydrogen, you can actually get hydrogen peroxide forming. If you take oxygen and react it with an alkali, you can form a peroxide. You can form sodium peroxide. And something like sodium peroxide would be, which is unusual, would be something like that, where the sodium's +1 and the oxygen is -1. Right? It's not a -2 like you'd normally think of oxygen. So peroxide is that -1 form. Okay? So oxidation numbers they're not charges, right? Like NH3, for example, it's a covalent compound. These are the nitrogen and the hydrogen are not ions, right? The hydrogen's not +1 and the N is -3, and they're stuck together from electrostatic charges. They are covalently bonded, and the oxidation number is, if you rip them apart, where would the electrons go? The nitrogen would pick up all 3 of them, and each hydrogen would get rid of its electron because that's what it wants to do. And it had priority over the nitrogen. So that's what an oxidation number is. Okay, now how do you go ahead and apply that understanding to chemical processes? So let me give you, this is our last little bit here. Okay, so in this question here, how can I tell if A, it's a redox reaction, and B, what reduced and what oxidized? You have to be able to look at your oxidation numbers before and then after, compare the 2 of them, and say this is what happened. Okay, so let me give you a couple of examples here. Okay, so the first example I'm going to do is now I'm not going to balance any of these reactions, okay? So they're going to be unbalanced chemical equations, but they're going to be chemical equations, okay, nonetheless. Okay, so I've got sulfur dioxide decomposing into octatomic sulfur and diatomic oxygen. So what happened? Is this a redox reaction? What reduced? What oxidized? So always remember that if a redox reaction occurred, one atom had to reduce and another atom had to oxidize. Okay? If you don't have that, well then, one, you might have done something wrong. You may have misanalyzed what you were doing. But if it doesn't do that, like an acid-base reaction will not show changes in oxidation numbers because it's just an exchange of an H+. It went from one place to another. It didn't change its actual oxidation number. So it's not a redox reaction. But in this one, if I go through each thing and I do it fairly quickly, I say to myself, what happened to each atom? So let's look at the atoms before the reaction, the sulfurs and the oxygens over here in sulfur dioxide. So assigning oxidation numbers to it. So sulfur and oxygen, higher priority goes to oxygen. Oxygens are -2. I have 2 of them, so therefore they contribute -4. That means the sulfur must be or have an oxidation number of +4. So that's what the atoms started with. And then they did this decomposition reaction, and then they formed these 2 things over here. What are their oxidation numbers now? Well, both of them are in their elemental form. Granted, they are polyatomic elemental forms, but they're still polyatomic. So they're still neutral and elemental. The charge here is 0. The charge here is 0. So whether I had 1, 2, 4, 8, 1,000, doesn't matter. Or they come out to 0. So the oxidation number of the sulfur in its elemental form was 0. The oxidation number of the oxygen in its elemental form is 0. And so what actually happened here? Well, this sulfur, look what the sulfurs did. So the sulfur atoms, and don't worry about how many we're going to do that next class when we balance chemically these redox reactions. Each sulfur went from +4 to 0. Now, okay, you might be able to say, well, that must have happened 8 times when we balanced this thing. But each individual sulfur went from +4 to 0. So how do you go from +4 to 0? So this guy reduced, and it gained 4 electrons. That's not the total, but each individual sulfur gained 4 electrons. To go from an oxidation number of +4 to 0, it had to have picked up 4 electrons in order to do that. So what did the oxygen do? Let's do it in a different color here. Let's do it in green. Each oxygen went from -2 up to 0 on the number line. So that is that guy, oxidized. Each individual oxygen lost 2 electrons. And of course, I'm talking about per atom, right? So each sulfur gained 4 electrons. Each oxygen lost 2 electrons. Now, the whole balancing of redox equations is going to try and make the number of electrons transferred equal to each other, because you can't have random electrons all over the place. So that's what we're going to do in the next class. But you have to understand what happened kind of behind the curtains of this reaction, which one oxidized, which one reduced. You can see that there are 2 halves to this reaction. One half is one atom reducing, and the other half is the atom oxidizing. In this case, they both happen to be in the same molecule, right? And so within that molecule, an exchange of electrons occurred, and they form these things over here. Okay, next one. Let's go back to that one that I had right at the beginning. So I had CH4 plus O2 goes to CO2 plus H2O. So let's assign oxidation numbers before this thing happened. Okay, so over here, before the reaction, so go through each one. So carbon and hydrogen, they're in a molecule. Carbon and hydrogen, who has higher priority? Hydrogen has higher priority. So hydrogens get +1. According to my priority list, there are 4 of them. That's a total charge of +4. The single carbon that's in there then must be -4. So carbons in methane have an oxidation state or number of -4. The oxygen is in elemental form. So each oxygen is 0. Okay, cool. That's before the reaction. So what about after the reaction? Okay, over here, carbon's now attached to oxygens. Okay, so they exchange partners. That's cool. So what actually happened here? So who gets priority, carbon or oxygen? Oxygen's higher priority. Oxygen has a charge of -2. Sorry, oxidation number of -2. I shouldn't say charge. It's a covalent compound. So it has an oxidation number of -2. There are 2 of them. That makes a total charge of -4. Single carbon then has to be +4. Oh, that's interesting. Carbon kind of got changed quite dramatically there from -4 to +4. How about over here in the water molecule? So who has priority, hydrogen or oxygen? Well, hydrogen has priority, and it's +1. There's 2 of them, that's +2. The single oxygen then has to be -2 to make that molecule come out to neutral. So none of these happen to be ions, right? So they're all coming out to neutral in the compounds. So what actually happened here? So let's look at what oxidized and what reduced. So I think, let's look at the carbon first. So the carbon went from -4 to +4. If it went from -4 on the number line up to +4, that means it oxidized. Okay, so I'll write oxidation. Well, it went from -4 to +4. How many electrons must it have lost if it was oxidizing? Well, that's a movement of 8 electrons, right? So carbon lost 8 electrons. Wow, that's a lot of electrons. So it lost 8 electrons per carbon atom. Well, what else changed here? Take a look at the hydrogen just for a sec. So the hydrogen over here was +1. It's still +1 over here. So the hydrogen didn't do anything. It stayed +1. It was +1 before, it was +1 after. Now, it changed partners, like it was bonded to different things. But in terms of its oxidation number, nothing changed in terms of its electronic structure. It was +1 before, it's +1 after. Didn't really do anything. Moved, but didn't change its oxidation state. So it wasn't really participating in the redox reaction. But what is the oxygen doing? The oxygen, right here, is going, well, it's 2 different places actually. It's going there, and it's going there. So the oxidation is going from 0 to -2. So it's a reduction. Now, each oxygen atom gained 2 electrons. Now, again, I don't want to get too much into this, but the number of electrons that transferred are going to be equal. The ones that are lost are going to equal the ones that are gained when we balance this overall reaction. So it's going to come out in the wash that this thing works out. So don't get too caught up right now on, well, what are you talking about? Like 2 oxygens over here and 3 over there, and which ones gained and which ones didn't. And you'll see once we actually balance the reaction that it actually makes a little bit more sense once you go into the process of balancing these equations. Okay? But you can tell that if you assign oxidation numbers before and after, you can kind of see which atoms did something and which atoms didn't do something. Last one. Okay, so last one is going to be, we're going to take permanganate. So MnO4 is permanganate. We're going to react it with ammonium, and we're going to make manganese plus 2 plus NO2 plus H2O. Okay, so did a redox occur, and which atom oxidized, which atom reduced? Assigning oxidation numbers. So the MnO4. So you can't just say, well, these are monatomic ions. It's not quite that simple because they formed a polyatomic ion. So kind of yes, but kind of no. So the oxygen assigned priority is -2. Scribble it up above. There are 4 of them. So that's a total charge of -8. So what charge must the Mn be in order to make the whole thing come out to -1? Okay, so the oxygens are contributing -8. The manganese must have been +7 to make the overall polyatomic ion come out to -1. Okay, NH4. So the N's and the H's, the H gets priority. The H's are +1. There are 4 of them. That's +4 total. The nitrogen, therefore, has to be a -3 in order for it to make the polyatomic ion, ammonium, come out to +1. Okay. Afterwards, you've got Mn as a monatomic ion, so it's +2. I mean, it's again, just rewriting the charge up above it. It's monatomic. So NO2. So nitrogen and oxygen, the overall molecule is neutral. So the oxygen has higher priority. It's -2. The nitrogen, therefore, has to be +4. There's 2 oxygens. 2 times -2 is -4. The nitrogen must have been +4 to make that a neutral molecule. And then last but not least, water. Hydrogen gets priority. It's +1. Water is really stable because both those atoms tend to be in the oxidation state that they like to be in. Hydrogen +1, oxygen -1. Okay, so, and that's why it tends to be non-reactive and pretty stable thing. So we've assigned oxidation numbers kind of all over the place. So what actually happened here? Okay, so what actually happened was the manganese from the permanganate went into the Mn+2, so it reduced. And because each manganese went from +7 to +2, each one must have gained 5 electrons. And then for, let's see, what oxidized then? So the oxidation, well, let's look at the oxygen first. -2, -2, -2. The oxygen didn't do anything. It stayed -2, so it's not the oxygen. Hydrogen, +1, +1. You'll tend to see that the things high on the priority list tend not to change their oxidation number a lot. You'll see that. In this case, the hydrogen and the oxygen didn't do anything. They're along to be bonded to other things. So actually what happened is the nitrogen, that nitrogen atom went from -3 to +4. So an oxidation number of -3 to +4. That is an oxidation. And each nitrogen atom, because it went from -3 to +4, must have lost 7 electrons. Okay, now, the last thing that's on the list here is, should be able to identify the oxidizing agent and the reducing agent. Okay, so first of all, what we've done is we've taken our oxidation numbers, been able to label everything before and after the reaction in order to see what thing reduced and what thing oxidized. And not only that, I got you to looking at, well, how many electrons did an atom lose or gain during that process. Okay, and that will help us out later on in kind of understanding these reactions later on, also with the balancing. But there are 2 terms over here that are super, super critical. Like there's terminology that you have to know. And one is called the reducing agent and one is called the oxidizing agent. And the reducing agent and keep this in mind, okay? Let's start with this. The word agent in chemistry means causes. Okay, so if you are an agent, you cause something to happen. So if you are a reducing agent, you cause reducing. Agents cause. So reducing agent causes reducing. Oxidizing agent causes oxidizing. Well, how do you cause those things in a redox reaction? You cause reducing by oxidizing yourself. You cause oxidation by reducing yourself. So if you're labeling the oxidizing and reducing agent, number one, you're always talking about something over on the reactant side. Okay, so you're talking about these things over here. So if I use this as my example, the oxidizing agent will be the chemical, and it's not by atom here anymore. You call it the chemical. So the oxidizing agent will be the thing that reduces so that it causes oxidation. So what thing up here reduced? Between those two chemicals, which one reduced? Well, this guy reduced. Therefore, this guy, this chemical right here, you would label the oxidizing agent. It reduced, causing an oxidation of something else. Okay, that's kind of weird because the terminology is backwards. If you reduce, you are the oxidizing agent. Therefore, that means that the other thing, the NH3, the ammonium, must have been, I'll do it in black because that's the only color that I haven't used. So this one right here would be labeled the reducing agent. Again, it's kind of weird, but if you remember that the word agent means causes, so therefore it's opposite. What you do is opposite to what you cause. So the oxidizing agent is the thing that reduces. The permanganate would be the oxidizing agent. The reducing agent would be the thing that oxidizes, and that was the ammonium contained the nitrogen that oxidized. So the ammonium would be referred to as the reducing agent. So if you said, during this redox reaction, ammonium was the reducing agent, it's telling you that something in the ammonium did the oxidizing during this reaction. Okay? And so that terminology, you'll hear it all the time. It will hopefully become just part of your regular chemistry vocabulary, because those are critical terms that you're going to hear all the time from your teacher and as long as you do chemistry. Okay, so that's our introduction to reduction oxidation and kind of the concepts of oxidation numbers and the principle of what is a reduction, what is an oxidation. You got to have both in order for a redox reaction to occur. And then starting to look a little bit more in detail of what happens per atom during a chemical process. So there's a bunch of things that are going to come out of this. Number one, first thing that we have to do, or the next thing I guess we have to do, is I want to show you how to balance a redox reaction. Like, how do you go about doing it? In that process, you'll kind of see the concept of half-cell reactions, which means that a redox reaction is actually two halves, put them together, and you come out to an overall reaction. But you can almost kind of think of them as two halves to an overall reaction. And that will help you out. After we do that, then we're going to start getting into that spontaneity concept of how do you know if the transfer of electrons will be in a spontaneous direction or not? Do these atoms want to do this exchange of electrons, and how do you figure that out? Beyond that, because we're talking about transfer of electrons, there is an electrical potential associated with electron movement from one atom to the other. If you're going to lose electrons and they're going to go over here to another atom, what is the electrical potential of those electrons to actually do that? And so we'll start actually getting into voltages and potentials for chemical reactions to occur and their spontaneity. And then last but not least, then we get into the actual electricity part of it all. Can we actually use electricity to cause these reactions? Can we actually get electricity from these reactions? If we're just talking about transfer of electrons, and electricity is the flow of electrons through a conductor, can we apply this chemistry to making a flow of electrons? And of course we can. And that's where batteries essentially come from. So we'll get into all of that later on in the process. But next class is going to be about balancing redox reactions and what's known as the half-cell method. So until then, I will see you, and hopefully this helped explain a little bit of what is redox and kind of gets you going in the right direction here for reduction oxidation reactions. So I'll see you next time.